Hello and welcome back to another episode of Math with Sohn. Today we are going to be doing a spring problem. So with this spring problem, we have a spring constant of 40 newtons per meter. It is attached to a surface and is going to be having a 0.25 kilogram block as shown. The block is brought to a position of 20 centimeters from equilibrium. So it's kind of like moving and compressing in 20 centimeters from equilibrium, allowed to oscillate frictionlessly back and forth forever. Fun. So if it's compressed, it's going to want to push backwards, and then once it stretches out, it's going to want to pull backwards, and it's going to boing back and forth from the 0 centimeters position. So draw a free body diagram when it is stretched to the position of negative 20 centimeters. That would mean that if it's over here, it will want to move this direction via the force of the spring, and you would still have the force natural, and you would still have the force of gravity as well. Okay? Determine the period of the spring block system. Well, the period of the spring block system would be equal to T is equal to 2 pi square root of m over the spring constant. Do we know the spring constant? We do. Do we know the mass? We do. Well, I guess this is pretty easy then. It would be 2 pi divided by, not divided, times the square root of the mass, which is 0.25, divided by the spring constant, which is 40 kilograms, Newton meters. And then if you do that calculations, you get 0.5 seconds. All right. Determine the max speed of the block. All right, now that will require a little bit more thinking. The maximum speed of the block is going to be involving the idea that the potential energy and the kinetic energy are going back and forth. All right, it's going to be at its maximum speed at equilibrium. Okay, and with it being at equilibrium, the potential energy would be equal to 0. The kinetic energy would equal as most as it possibly can. But more importantly, the U of the spring will equal the K of the spring. As far as the maximum values. The U spring max will equal the K spring max. All right? And they're going to oscillate back and forth and change back and forth. Well, the U, or the potential energy of the spring, is equal to 1/2 kx squared. And if that would have to equal the maximum of the spring, well, that would equal 1/2 mv squared. And we're looking for the maximum velocity. We know the spring constant, so we would have 1/2 our k, which is 40, times our displacement, which is 0.2 squared, would have to equal 1/2 our mass, 0.25, times the velocity squared. You can divide by 1/2, and they would cancel out. You can divide by 0.25, and you get v will equal the square root of 40 times 0.2 squared divided by 0.25. And when we do that calculation, you get a velocity of 2.5 meters per second. All right? Derive an expression for the displacement of the block as a function of time. Well, in the previous episode, we learned that there is a formula for that. It's called x of t is equal to the amplitude, or the x displacement, cosine of omega times t, and that omega is the period, the 2 pi divided by t, the 2 pi divided by the period. So, with that in mind, we can just plug in our amplitude, which is our displacement, cosine of 2 pi divided by our t. Have we figured out the t yet? Yes, it was 0.5 seconds. And then we can multiply that by time. So if you do a little bit of simplifying here, 2 divided by 0.5 ends up being 0.2 cosine of 4 pi t. That would equal your x displacement. Okay? Or your x as a function of time, more specifically. All right, the next thing I want to do is talk about, on a graph, plot the displacement, velocity, and acceleration on a block versus time graph. Okay, so we are going to put time here, and time here. And here we would put our displacement, so this would be our change in x. Here we're going to put our velocity, which would be essentially our meters per second. And here we'll put our acceleration, which would be meters per second squared. So on the thing, on this goes with any oscillation. Assuming you start at the top, it is going to kind of do this number, all right? Where it's going to start out in the positive direction. That was when the spring was to the right. And then it's going to go backwards and forwards. So it's going to go from positive to negative and then back up. And these should be about the same dippingness, all right? And it will slow back down as it reaches that furthest to the right or furthest to the left. The velocity is going to be changing constantly. And you got to think of it. We were in the positive direction. We were over here in the positive direction, and then we got pulled to the left. So if we're getting pulled to the left, that would indicate that the velocity started out 0, but it was pulling us to the left. And then it started to slow back down, and then it started pulling us to the right, and so on and so forth. So it is actually a sine graph where the displacement is a cosine graph. And for those of you that know calculus, it's actually a negative sine graph. The derivative of cosine is negative sine, so that's where that's coming from. And then the acceleration, if you think of the acceleration, we started with it moving us from here to the left. It was picking up speed. It started accelerating to the left, and then it moved it from the left, and then it started slowly pulling it to the right, which is why it looks more like this parabolic shape. All right? Next up, we got plot the potential and kinetic energy, and this is going to be the last thing we do, of the graph. Well, if you think of it starting on this side right here, all of that energy was stored up and it wants to shoot the other direction, so it's going to start with potential. We're going to do potential in blue. It started up here for potential, and then it kind of does this number. Okay? Notice how I am not going below the x-axis. So the potential started up high, and then it went to 0 at equilibrium, and then it went back. So started up high, 0, then up high again. 0, then up high again. This is the potential. 0 at potential, high for potential. 0 at potential, high for potential. Back and forth. You don't have negative potential. The kinetic energy started at 0. Blue. Kinetic we're going to do in black. And it's going to be a mirror image of it. So the kinetic started at 0 and then got really high in the middle, then ended at 0. Back and forth forever. Okay? That's going to do it for this one. In the next video, we're going to be talking about 2 spring systems. Look forward to seeing you then. Stay positive, my friends. Bye.